Learn something new every day for everyone. Have something you want to learn? Submit yours at LumoLab.org.
Humans don't start thinking from scratch every second. As you read this sentence, you understand the word sentence based on the words that came before it. Traditional feed-forward neural networks can't do this. They have no memory. To solve this, we use recurrent neural networks, or RNNs. Imagine a network containing a loop. This loop allows information to persist.
If we unroll this loop, the mechanism becomes clear. An RNN is actually multiple copies of the same network, chained together. Each copy passes a message to its successor. This chain-like nature reveals that RNNs are intimately related to sequences and lists. However, standard RNNs struggle as gaps widen. Consider predicting the last word in "the clouds are in the sky." The gap is short. The RNN handles this easily. But what about "I grew up in France," followed by a long paragraph, ending with "I speak fluent French"? To predict French, the model needs context from way back at the start. As that gap grows, standard RNNs become unable to connect the information. This is the long-term dependency problem.
Long short-term memory networks, or LSTMs, were introduced by Hochreiter and Schmidhuber in 1997 specifically to solve this. While a standard RNN repeating module contains a single layer, usually a tan function, the LSTM is different. It contains 4 interacting layers. Don't be intimidated by the diagram. Let's break down the superhighway that makes this possible.
The core of the LSTM is the cell state. It's this horizontal line running straight through the top of the diagram. Think of it like a conveyor belt. Information can flow straight down the entire chain, largely unchanged. This is how we keep France in memory for the long haul. The LSTM carefully regulates this flow using structures called gates, which can add or remove information from this conveyor belt.
Step 1 is the forget gate. We must decide what to throw away from the conveyor belt. A sigmoid neural layer looks at your previous output and your current input. It outputs a number between 0 and 1 for each number in the cell state. 1 means keep this completely. 0 means get rid of this. If the context changed, say the subject of the sentence changed gender, this is where we'd forget the old gender.
Step 2. What new information do we store? This happens in 2 parts. First, a sigmoid layer, the input gate, decides which values will update. Second, a tanh layer creates a vector of new candidate values that could be added to the state. We're preparing to add the new gender information to replace what we just forgot.
Now we actually update the cell state. We multiply the old state by our forget factors, physically removing the things we decided to forget. Then we add the new candidate values, scaled by how much we decided to update. This math, multiplication to forget, addition to add, is what generates the new cell state.
Finally, we need to produce an output. We don't just output the raw cell state. First, we run the cell state through a tanh to push values between -1 and 1. Then we run our inputs through a sigmoid gate to decide what parts of that state we want to expose. We multiply them, and that filtered version is our output. We might know a lot about the subject, but if the next word is a verb, we only output the information relevant to verbs.
While that's the standard LSTM, researchers use variants. One popular version adds peephole connections, allowing the gate layers to look directly at the cell state. Another couples the forget and input gates, meaning we only forget old information, specifically when we're inputting new information in its place. These tweaks allow the model to adapt to specific types of timing tasks.
Thanks for watching, and keep learning.